Welcome to part 2 of the chapter 4 lecture. We just spoke about the number of bonds that different elements will want based on how many more electrons they need to become more stable. And there's this convenient rule of 4 for most elements. Now, hydrogen will only have one bond maximum, and boron will have a maximum of 3 covalent bonds because he has 3 valence electrons to share. Starting with carbon, with his 4 valence electrons, and moving up, what we're going to find is that the number of bonds an atom forms plus the number of lone pairs of valence electrons will add up to 4. So let's take a look. Carbon has 4 valence electrons to share. He needs 4 more to be like his nearest noble gas. So he wants 4 bonds. Once we give him those 4 bonds, he's used up all of his valence electrons. So now there are none left over to draw as dots in a lone pair. 4 plus 0, 4 bonds, plus 0 lone pairs adds up to 4. Nitrogen needs 3 more electrons so that he can have an octet, or to have the total number of electrons as his nearest noble gas. So he will add 3 bonds to get to have shared custody of those 3 electrons. Once he does share 3 electrons for those 3 bonds, he still has 2 valence electrons left over. He's in group 5A. Well, those extra 2 valence electrons will be a lone pair. 3 bonds plus 1 lone pair adds up to 4 again. Oxygen's in group 6A, so he starts with 6 valence electrons. He just needs 2 more. So he'll make 2 bonds. When that's done, he's used up 2 of his original 6 valence electrons. That means he still has 4 left. Those get drawn as 4 dots in 2 lone pairs of electrons. Well, in his case, 2 bonds plus 2 lone pairs adds up to 4. And finally, our halogens, they get represented by the letter X because we have fluorine, chlorine, bromine, and iodine, and they're all equally reactive. We use them all a lot. So we often represent them with the letter X. Those guys are in group 7A. They have 7 valence electrons. They need 1 more to be stable. Well, that means they're just going to share 1 of their 7 valence electrons in a bond. That leaves 6 left over that are non-bonding electrons. We'll put those around as 6 dots, and we'll see that we have 1 bond plus 3 lone pairs of valence electrons. Again, that adds up to 4. I want you to know that it's not just these elements that are going to be appearing. In fact, what we'll find, if I can escape out of this, if I hit it, we'll get this box, but that's okay. I want you to know that it's not just the guys in the top row that follow this pattern. Underneath carbon, we have silicon and germanium, but we'll see silicon a lot. He does the same kind of bonding as carbon. Remember, same column, vertical column, same group. They do similar types of bonding. Both of those elements, the carbon and the silicon, will want to form 4 bonds, preferably 4 covalent bonds, as opposed to taking 4 electrons from the middle. Everybody in group 5 will see nitrogen and we'll see phosphorus a lot. Those guys are going to form 3 bonds with 1 lone pair. We will see oxygen and sulfur a lot. You may see selenium in the homework. So, well, no, because I'm doing the homework. If you do the optional Learn Smart assignment, then you will see that those guys want 2 bonds and 2 lone pairs. And then again, all of our halogens will make 1 bond with 3 lone pairs of electrons. All in the final goal of being like these noble gases in the same row. Metals, we go up, we go backwards because they lose electrons. Nonmetals and metalloids, we go forwards because they add electrons. Okay, so now that you know that it's not just carbon, nitrogen, oxygen, that we're looking at the guys underneath them too, silicon, phosphorus, and sulfur, let's go back to what we have going on here. And I'm going to get rid of this box again. So, carbon, 4 valence electrons. He wants 8. He'll get those if he shares his 4 valence electrons in 4 bonds. Nitrogen already has 5 valence electrons. He just needs 3 more. He will form 3 bonds to have a total of 8 valence electrons in his outermost shell. Those remaining 2 electrons that he didn't use to form bonds, those will remain a lone pair of electrons, 2 dots that get left on the symbol. The number of bonds are going to equal the number of electrons that are wanted. The number of bonds an atom wants, you can figure it out based on the number of electrons they want. And this concept is exactly the same as what we did with the ionic bonds. Just like we said, oxygen, group 6A, he'll make a -2 charge because he's going to gain 2 electrons. The only difference is now that oxygen's with other nonmetals and metalloids, he can't get a full negative charge. He can just borrow electrons sometimes, but it's still going to be 2 that he wants. Instead of getting a -2 charge, oxygen's going to form 2 covalent bonds. Same concept as chapter 3. The number of electrons they need to be stable will equal their charge when they are in ionic bonds, and the nonmetals and metalloids, when they're with other nonmetals and metalloids, they are going to have that number of covalent bonds based on how many electrons they need to be stable. Nonmetals and metalloids with 4 or more valence electrons, so starting with carbon, they will share enough electrons to sometimes have 8. It's shared custody, just like you can imagine kids with shared custody. This time the atoms are sharing custody of those electrons. When fluorine, a nonmetal, hangs out with sodium, a metal, fluorine just takes an electron from sodium. Then they both have the same number of electrons, whether you think of it in terms of valence electrons or total number of electrons. They have the same number as neon, their nearest noble gas. And they are permanently happy as the cation, sodium +1, and the anion, fluoride -1, in an ionic bond. Metal with nonmetal, the electrons get exchanged from the metal to the nonmetal. Everybody's happy. When 2 fluorine atoms hang out with each other, so there's no metal around, however, neither is willing to give up an electron. Instead, they will each share 1 of their valence electrons. If they share 1, they get 1 from the other atom. They share 1 electron so they can get the 1 electron that they need. These 2 electrons, the one they share and the one they borrow, will be in a covalent bond. Notice how we do a straight line for the covalent bond between atoms. We don't leave it as 2 dots. We replace it with a solid line. It represents the 2 shared electrons. Many molecules contain more than just single bonds. Double bonds and triple covalent bonds exist too. A double bond represents 4 electrons. So we start with a single line, that's 2 electrons, and then we double it up. We add a second line, that's an extra 2 electrons. A triple bond represents 6 electrons, 2 + 2 + 2. We have a total of 6. There are a few elements that can do double bonds. Carbon, obviously, nitrogen, oxygen, sulfur, selenium. Those guys do double bonds. It's much more rare for triple bonds. The only elements I'm aware of doing triple bonds are carbon, and nitrogen. So what we find interesting then is that there's a lot more limitation when it comes to doing 3 bonds between atoms. A lot of elements are just going to form single bonds. The other thing that I need you to know is that I lost my train of thought. 1 second. Got my train of thought back. It is the fact that there is no quadruple bond that has been discovered yet. So no 2 atoms share 4 bonds with each other. That doesn't exist. 3, a triple bond is the maximum. And I've only seen that between 2 carbon atoms, 2 nitrogen atoms, or a carbon and nitrogen atom. All right, let's learn about representing our covalent compounds. We've talked about chemical formulas before, right? Where we do things like H2O and NaCl. Those kinds of formulas tell us the identity of the elements and the number of each atom of those elements in that particular unit. We're learning a new term now with molecule and molecular formula. The molecular formula comes into play when we have covalent bonds, but it's still the same idea. A formula is a formula. It's something like NH3 or H2O. Notice though that when I write NH3 and H2O, I don't tell which atoms are bonded to each other. I just tell you which elements there are and what the total number of them are. There's other models that can be used. So the first one is our molecular formula. Here it's PH3, a phosphorus and 3 hydrogens. A structural formula is an example like this one, where we have the carbon atom and he has 4 single bonds to 4 hydrogens. The space filling model, here's the one we've seen with water before, where the oxygen is closely located to the 2 hydrogen atoms. That is opposed to the ball and stick model, where we show a little bit of space to represent the bonds between them. This is more what would occur in nature. This is more to help us see which bonds are attached to each other a little bit more easily. This last one, this is a brand new term for you, a Lewis structure. That's what we're going to be learning how to do next. The only difference between a structural formula and a Lewis structure is that we include these dots. We include the lone pairs of electrons. Structural formulas, sometimes we put them in, sometimes we don't. But with a Lewis structure, we are required to draw in the lone pairs of electrons on any of the atoms that have them. The Lewis structure is really great because it shows us how the atoms are connected and the location of all bonding and non-bonding valence electrons, or the lone pairs. So I've got my bonding electrons represented with straight lines, and my non-bonding electrons that are still there, they're still hanging out, they're just not part of the bond. We have those drawn in as dots. That's the neat thing about the Lewis structures. All of my electrons that are involved in the bonding with this molecule are shown in the structure. Let's learn how to do them. I'm going to give you some general rules and tips, but before I do, let me let you know some things. Number one, you're likely to either have learned some of this before, for some of you who have had chemistry before, or you may go online and watch some videos on how to do this. And I'm going to tell you right now, a lot of those are going to explain it in a different way than how I do. And one of the main things are going to be, they're going to have you add up all the valence electrons. And then some of them are going to have you draw in all the dots first, and then take the dots and turn them into straight lines. I don't do it that way. And let me tell you why. From not just from teaching it and tutoring it and seeing what works better for students, but also the fact that we don't, as scientists, actually draw in dots and then replace them with lines or anything like that. And I decided rather than having you guys do something that no one who actually knows what they're doing would do, I might as well just teach you guys the same way that all of us who already know chemistry, how we do it. Once we're comfortable with it, why don't we just get you guys up to speed, okay? And last semester, I did survey everyone. I asked the ones who didn't do so well on the assignment where they were looking at how to draw the structures. And I asked the ones who were really good at it, where they learned to do the structures. And except for the student who went to UNC Chapel Hill and learned it there, and so already knew how to draw them, everybody else that did really well with it said that they watched my videos and did the style that I was teaching. So I hope that's maybe a little bit of encouragement for you to keep watching and give my method a try. If you don't like it, if it doesn't work for you, feel free to go online and watch some other YouTube videos for other ways to draw the structures. All right, here we go. General rules and tips for drawing Lewis structures. First of all, you're only going to draw valence electrons. We are going to be using the same pattern for everybody in the same column, in the same group. As we go down, they're going to have more and more electrons, but the electrons that are on the inside, closer to the nucleus, they're not involved in bonding. It's only the ones on the outside, and that's all I care about for my Lewis structures. So no more thinking, carbon has a total of 6 electrons, but he only has 4 valence electrons. He's in group 4A. You'll never draw starting him out with 6. It's just not done, okay? And silicon has even more than that, but again, we just start with 4 valence electrons. Number 2, before you finish, you want to make sure that every atom except hydrogen and boron has 8 valence electrons. Hydrogen will only have 2 total, one that he shares and one that he borrows. Boron will only have 6 electrons, 3 that he shares, 3 that he borrows. Everybody else, starting with carbon, when they share their valence electrons and borrow the other atom's electrons, they should add up to 8 total. I recommend that you start with single bonds between the atoms. Then, if you need to draw a double bond or a triple bond, you'll do that. And then I personally finish with the lone pairs of electrons. Single bond first, if necessary, double and triple bonds. Finally, fill in any remaining non-bonding electrons. We're going to place the elements that want the most bonds in the center of our drawing. Carbon, again, carbon's king. Carbon should always be given 4 bonds first. Next, you want to try to give nitrogen 3 bonds and oxygen 2 bonds. Finally, you're going to place any hydrogens or halogens, the fluorine, chlorine, bromine, iodine, the guys who only want 1 bond. You're going to put those guys around the center atoms to make sure that the center atoms get the number of bonds that they want. They're great for that. They're the arm candy, making sure that the guys in the center are happy. Oh, I didn't have that on the thing yet. So how to draw it. First, I want you to determine how many bonds each element wants. So we talked about that before. You count the electrons over to the nearest noble gas, or you subtract the group number from 8, however you want to do it. Figure that part out first. Then you're going to arrange the atoms with a single bond between each pair of atoms. Tips: the first element in the molecular formula usually goes in the center, unless it's hydrogen. So remember, hydrogen gets 1 bond, he'll never be in the center. Number 2, the element that wants the most bonds or the most electrons, so he's going to make the most bonds, he usually goes in the center as well. For CH4, the carbon is king. Carbon wants 4 electrons, so he goes in the center. Then those 4 hydrogen atoms go around him. I fill it in with single bonds to each one, and I have a good structure here. Now, what would not work? Something like this isn't going to work. This hydrogen cannot form two bonds. He's not going to be between two atoms. Also, carbon's not happy. If he just has three single bonds, we've got an upset king on our hands. Make sure carbon gets 4. We're going to have our hydrogens and halogens around the outside since they only form one bond. Pause this for a second. Oh, foreshadowing. So we're going to use the common bonding patterns from figure 4.7. It's on page 110 of your text, and the tips from the previous slides to arrange the atoms. This time our molecular formula is CH5N. Okay, so let's think about this for a second. How many bonds does carbon always want? He's in group 4A. 4 plus 4 equals 8. So carbon always wants 4 bonds. Hydrogens. Each hydrogen gets only 1 bond. Nitrogen. He's in group 5A. He needs 3 more electrons to have 8. Okay, so he wants 3 bonds. Who's going to go the most in the center, and then who's going to be off to the side? We're going to put carbon in the center. Nitrogen gets to be in the center too, but first we'll make sure that we give carbon 4 bonds. I've got 5 hydrogens to share. Let's make sure that carbon gets 3 of those. Then nitrogen can have the other 2. If I set something like this up, we're going to have an issue. Nitrogen only wants 3 bonds. He's not going to want to have 4 atoms around him. Let's fill in the single bonds. Oh yeah, this is really looking good. Carbon's got the 4 bonds that he wants. Nitrogen has the 3 bonds that he wants. Excellent. We've got our 4 atoms around carbon because he wants 4 bonds. We've got our 3 atoms around nitrogen because he wants 3 bonds. Now something's missing. If I add these up, I see 2, 4, 6, 8 valence electrons around carbon. The 4 that he brought to the party because he's in group 4A, plus the 4 that he's borrowing from the hydrogens and the nitrogen. He's used up all 4 valence electrons in those 4 bonds. But nitrogen, he has the 3 bonds he wants, but he's missing the other 2 electrons that he came to the party with. He's in group 5A. He's used 3, but he still has 2 left over. The other thing I can check is if I add up for each single line, it's 2, 4, 6. He's missing the other 2 that give him the octet. So I need to draw in a lone pair. Here we go. Now it looks good. I've got the 2, 4, 6, 8 valence electrons around nitrogen. And for those of you who have seen the method of adding up all the valence electrons, you'll find that when I count these all up, which is on the Learn Smart assignment, where they ask you for the total number of valence electrons per molecule, you can add it up. Each straight line adds up to 2. And then of course we have the 2 dots in the lone pair. So 2, 4, 6, 8, 10, 12, 13, 14. 14 valence electrons in this molecule that have all been accounted for. And everybody has the bonds they want. Yay. Let's see what happens next. Well, let's say we had 2 atoms next to each other that with a single bond, they didn't get enough valence electrons around them. Well, then what we can do is if I don't have enough and my neighbor doesn't have enough, we get to go ahead and make another bond. We started with one bond that represents 2 electrons between every 2 atoms that are bonded together. If neighboring atoms want another bond, give it to them. This will require forming a double or triple bond. Oxygen and sulfur, they can make double bonds, but not triple bonds. Carbon and nitrogen, they make double and triple bonds to each other or to themselves. So 2 nitrogen atoms or 2 carbon atoms, or between nitrogen and carbon, we can get a triple bond or double. All right. And then lastly, we place any remaining valence electrons, non-bonding electrons around the elements. So I kind of jumped the gun there when I helped you do it on the nitrogen. I just didn't like the look of leaving that particular molecule without the lone pair of electrons. Let's do another one like that. Let's draw the Lewis structure for nitrogen. And remember, when I say nitrogen now, and we're talking about an individual molecule, it's going to be diatomic, 2 atoms in a molecule of nitrogen. You can also call it nitrogen gas if you want, because most of the time he's a gas. He's a real gas. He's so funny. Okay, sorry, that's old-fashioned. So I start with my 2 nitrogen atoms and I give a single bond between them. Okay, well, he's in group 5A, right? So didn't he want 3 more electrons? So he wants 3 bonds? Oh, well, neither one of them's happy right now, right? Okay, well, let's give him another bond. And when I hit this down arrow, we might get both bonds at one time. Let's see what happens. How many more electrons does each nitrogen need in order to be like its nearest noble gas, or to have an octet of valence electrons? We're going to draw that number of bonds. They each want 3, so we're going to have a triple bond. Now they're both happy. Both of them have the 3 bonds that they want. Again, though, this is not done because I don't have 8 electrons around them both. They have the bonds they want, but they each also get 1 lone pair of electrons. They each came with 5, right? So I've got 1, 2, 3 coming from this nitrogen. He'll need another 2 dots drawn in. And this nitrogen over here, he started with 5 valence electrons. He's sharing 3 of them in these 3 bonds. 1, 2, 3. He needs 2 more dots to represent the 5 valence electrons he started with. And there we go. I want you to get really familiar with seeing carbon with 4 bonds and no lone pairs. Same with silicon, he's underneath him in group 4A. 4 bonds, no lone pairs. I want you to get familiar with seeing nitrogen and phosphorus with 3 bonds and 1 lone pair. I want you to get familiar with oxygen, sulfur, selenium, the guys in group 6A, with 2 bonds and 2 lone pairs. And I want you to get comfortable with seeing the halogens, fluorine, chlorine, bromine, iodine, with 1 bond and 3 lone pairs. And you know what? I just remembered last semester I put all this down on a piece of paper and then I posted it, I think. So I should be able to do that again this semester. It'll be a cheat sheet for you. And I'm hoping you'll use that and give me some really great Lewis structures for your assignment for this chapter. There's one more that I want to do before we go on, because so far we did have that one where carbon and nitrogen were in the same structure, but I want to give you another one where we can have 2 atoms in the center. And so we're going to switch over now to my other camera. I'll be right with you. Let's do a couple where we have 2 carbons in the center, because this is pretty common as well. We're going to do, let's say, how about C2H6. Okay. This time I'm going to put 2 carbons in the center. I have 6 atoms of hydrogen to place around them. Well, this carbon has one bond. Carbon is in group 4A. So he starts with 4 valence electrons. Okay. He wants 8 total. 4 more electrons equals 4 more bonds, or 4 bonds. Okay, so he's got 1. We could give each carbon 3 hydrogens. They don't mind splitting it in half. I don't ever want to give carbon 5 bonds. He doesn't have enough valence electrons to share. So here's the 1, 2, 3, 4 that this carbon came to the party with. Each hydrogen is sharing 1 electron. And this carbon over here is sharing 1 electron with this carbon. Now I see that I have 2, 4, 6, 8 total electrons that this guy has at least shared custody of. I don't leave 2 dots. Please don't leave 2 dots in your drawings. In fact, you know what? That's going to be the passcode for this part 2 of the video. Our passcode is don't leave 2 dots as the bond. I don't want to see this. I want to see this. Okay? I also don't want to see this. I want to see this. Okay, so that's our passcode for this video. Don't leave 2 dots as the bond. All righty. Now let's do one that's a little bit not similar. Let's do C2, and this time let's do Br4. Okay, the 2 carbons, they want the most bonds, so they'll go in the center. Carbon wants 4 bonds. Bromine is in group 7A. He only wants 1 bond. He already has 7 valence electrons. 1 more will get him to 8. Okay, so we'll make sure that each bromine is a single bond. Well, we've got 4 to share this time. These guys are like, okay, we can be fair. We'll each get 2, because it's not very nice to give one of them 3 and the other guy 1. So let's give both over here. If you decide to do it straight up and down, that's fine too. I'm just going to go ahead and automatically draw it the way that it exists in nature, which would have these guys on angles. All right, let's check and see. Are the bromine atoms happy? Yeah, the Br are happy with 1 bond. Is carbon happy? Not with just 3 bonds, no. C wants 4 bonds. Well, 2 carbons want another bond. Let's give it to them. So here we go. Instead of a single bond, we're going to put a double bond, and then we'll still do our single bonds to each of the bromine atoms. 2, 4, 6, 8. 2, 4, 6, 8. Those carbons are happy now. The bromine are happy with 1 bond, that's right. Okay, then what's left? Well, the bromine atoms will only do a single bond, which is good because my carbons don't want 5 bonds. but they came with 7 valence electrons. That means they've used 1 for this bond, and they have 6 left over. I'm filling them in like a picture frame, and I have to do it for every single one of these bromine atoms. Notice how I put the dots around the outside. I don't do something like this. I put the dots around the other 3 sides that don't have the bond. And there we go. The bromines now have 6, 7 that they started with, plus the 1 they're borrowing, makes 8. Last one, I'll do it a little more quickly. Let's say we have C2I2. 2 carbon atoms in the center. Let's be fair, we'll give them each 1 iodine. All right, iodine's happy. He's in group 7A, so he wants 1 bond. Carbon, 4A, he wants 4 bonds. Well, let's give it to him. 2, 3. So now that carbon has 1, 2, 3, 4 bonds. He's happy. This carbon has 1, 2, 3, 4 bonds. He's happy. Iodine atoms, they're happy with 1 bond, but they have leftover electrons, just like the bromine. We're going to give it to them. And we're done. Okay. So that's how we do Lewis structures when there's more than 1 central atom. Especially, we'll see 2 carbon atoms pretty often, because we're going to see these again a little later in chapter 4. That'll be part 3 of the video for this lecture presentation. The last thing I want to do on this part of the video is how to name covalent compounds. How do we name them? Well, remember my Super 7 or Brinklehawk. These 7 diatomic molecules go by the element's names. So if the reaction is with oxygen, it's with O2, not just O. Some of you are going to get this wrong on the test, and it's going to be a bummer because I'm going to ask you for the formula for oxygen, and I'm going to want O2. Or better yet, I'm going to put down O2 and ask you for the name. And unfortunately, some of you are going to say it's dioxygen or dioxide or something like that, when it really is just oxygen. O2 is oxygen, not dioxide, not dioxygen. It's just oxygen, okay? All right, now here we have a nitrogen tossed in. We're going to name these as well. The naming for covalent compounds is different than the naming for ionic compounds. That's why the very first thing I want you to always do when you're given a when you're given a chemical formula, I need you to figure out first, is it ionic or is it covalent? The naming is different. With covalent molecules, we're going to use prefixes, words, well, a few letters that are going to come before the names like oxide and stuff like that. Okay, so watch what happens. We're going to name the first nonmetal by its element name, just like we did with the metals. The second, though, the second element, his name is going to end with IDE. Well, that sounds really familiar too, doesn't it? So far, it's similar to what we did with the ionic compounds, but there's going to be a change. So we're going to start both of these by saying nitrogen oxide. First element's nitrogen, second one's oxide. But obviously these are 2 different molecules, so there's got to be something more to it. Unlike with ionic compounds, where we ignored the subscripts when we named them, this time we're going to tell people what the subscripts are. How do we do that? Well, we use these prefixes. You can check them out in table 4.1 on page 120 of your textbook. The prefix mono is usually omitted, except when we start talking about oxygen. So CO is carbon monoxide, NO is nitrogen monoxide. Sometimes it's just nitrogen oxide. And so mono means one. If I have one oxygen, it's monoxide. If I have two of something, I use di. And so you've probably heard of carbon dioxide. I don't say monocarbon, but I do point out that there's two oxygens and say dioxide. If there's three, then I say tri. Three oxygens, trioxide. If there's four, now here's one that you probably are less familiar with, tetra. Tetra means four when it comes to naming covalent compounds. Tetra plus oxide. This time we're going to drop that A and just make it tetroxide. Okay. And then it goes from there. There's pentoxide, because penta is 5, and there's hexa and hepta. Here they are. I think of my 5 pentagon is a 5-sided drawing, so that helps me remember that 5 is penta. But you guys can have this list. That's the nice thing about taking this class online. There's got to be some perks, right? So you have an open book test for this, and you can hang on to those and keep them handy during any assignments or the tests. NO2, it's not just nitrogen oxide, it's nitrogen dioxide. N2O4, not just nitrogen oxide, it's dinitrogen, because there's 2 nitrogens, and then 4 oxygens becomes tetroxide, dinitrogen tetroxide. And it's going to have different properties than nitrogen dioxide, who has different properties than just nitrogen oxide or nitrogen monoxide. Everybody has a different property, and it can be life or death. Remember, carbon monoxide, CO, with 1-to-1 ratio between the carbon and oxygen, that'll poison us. We can die from carbon monoxide poisoning. But carbon dioxide, 1 carbon, 2 oxygens, heck, that's in my lungs right now. I'm breathing it out as we speak. So it's a matter of life and death, if you think about it. And I want to make sure that I say the right compound when I'm naming it. This is where I'm going to leave off with the second video, because the next section of chapter 4 has to do with a whole different concept than what we've done so far. It's going to be very handy that you can draw the Lewis structures. So that's where we'll be starting first. And being able to do the names is a great thing to do as well. But we'll address this new topic in another video. Thanks for watching, and be sure to do this part of the participation quiz for chapter 4 as well. Okay, bye.